In this video, I want to show you a form of proving two sets are equal. In this version, what we do is go through a chain of equal sets. Perhaps we have a set on the left-hand side is equal to a set on the right-hand side that we're trying to prove, and we're going to link those through this chain of identical sets using so-called set identities. Now, let's do an example right here. Let's just look at it first. Here is this, the complement of A intersect B union with the complement of B is equal to B intersected with the complement of A. Now, if I look at that, I see it's not obvious at all that this is true. We are going to show that it is true. Now, one technique for proving it is that we could assume an element is in the left-hand side and prove that it is also an element in the right-hand side. We could start with those things, use set definitions, and then do a bunch of logic and then translate out of the set definitions at the tail end to show if it is an element in the left-hand side, it must also be in the set in the right-hand side. Then we would say, suppose an element is in the right-hand side, use set theoretic definitions to translate out of set theory into logic, then do a bunch of logic, and then show that it is in the left-hand side, get out of the logic, get into set theory using definitions, and then we have shown if it's in the left-hand side, it must be in the right-hand side. If it's in the right-hand side, it must be in the left-hand side, and thus the two sets are equal. Now, for this one right here, that takes approximately 40 lines to do. We're going to show this one quite a shorter version of a proof, but we will be using set identities to do that. And those are theorems that have already been proven in the technique that I just described. All right, so let's start working on this example. Here we have our left-hand side. Here we have our right-hand side. And coming in here, we want some sort of different versions of this set right here and the sets to follow that transform from this form to that form right there. How are we going to do it? Well, let me just look first at the original version on the left-hand side here, and I see a complement of a union. When I see that, and I see the right-hand side doesn't have any complement sitting on the outside, I want to move this complement somehow to the inside of this expression. Easiest way to do that is with the Set De Morgan identity. We have, instead of having a complement of a union, what we now have is the intersection of two complements. So we now have the original expression on the left-hand side is the same as the complement of A intersect B intersected with the double complement of B. Now, I look again at my target down here. The right-hand side has no double complement, yet the form that I'm staring at right here does have a double complement of B. Let's get rid of that. So, using the set double complement property, I have replaced double complement of B simply with B. So that's our next step. Now, we still have a complement of A intersect B in the front of this right here that doesn't look much like what I'm aiming for in this target. So I'm going to use Set De Morgan one more time to put this set complement right here inside. We do that, now we have, instead of the complement of A intersect B, we have the union of the complement of A with the complement of B. And I like that right there. Now, the next step right here is a little bit funny. It's not so obvious. We actually could delay it, but I like it this way. I notice that in my target right here, B occurs first, and yet, where I'm staring at it right now, B occurs second in this intersection. So all I want to do is swap from this form right here to put B forward. That's just using the set commutativity property, and now I have B intersect the complement of A with the union of the complement of B. We're almost there. Now what I'd like to do is to use a distributivity property of this intersection over that union to now express this thing as a pair of unions. So let's use that distributivity property right here, and now we have the union of two sets. One is B intersect complement of A. Goodness gracious, look, that's our target. Union with something else, and that's B intersect with the complement of B. Now, looking again forward to our target, what we see is if we could get rid of this portion right here, we would be done. How could we do that? Stare closer at B intersect the complement of B. Can anything be in B intersect the complement of B? It would say it's both an element of B and it's not an element of B. So in fact, this expression right here is no more than the empty set. We have a set identity that says that any set intersect with its complement is the empty set. So we have this now, and we also realize that any set, for example, B intersect complement of A, union with an empty set is the same as that first set. So we can erase this portion right here because anything union with an empty set is what we started with. And that's our last step right here. We call it set computation, another set identity, and we end up with this. So we have gone through a chain of equalities, starting with our left-hand side, ending with our right-hand side, and this is a technique, and took us here 8 steps to prove this. As I said before, we weren't forced to prove it this way. We could have gone through using translation from set definitions into logic, do some logic, and then translate out of logic into set definitions to prove this, but it would have taken a great deal more work. So this shows you the benefit of knowing these set identities. And by the way, what we have just established right here is a new set identity, namely that these two forms right here are equal, and therefore on a subsequent proof we might want to use that as a set identity.